Hey, good afternoon, 61C. Finally got some rain. It's good. Okay, so it's kind of second part of the lecture on thread-level parallelism and OpenMP. So just to remind you what we talked about last time, there's been this big change in technology that meant that individual transistors aren't getting faster, and that meant that single processors aren't really getting much faster. And so these days, if you want fast code, you have to write parallel code. So sequential software is slow software. And we looked at, a couple lectures ago, looked at SIMD extensions. Last lecture, we started looking at MIMD, multi-threaded programming. That's really the only way to get higher performance these days, is to do some kind of parallel processing. We looked at multi-threading inside a core, which is a way of increasing utilization. Have one processor core run two hardware threads at the same time and switch between them to try and keep things busy. We also talked a bit about synchronization, which is a very important component when you have multi-threaded programs. Different threads of control, two processors running separate pieces of a program have to coordinate. And they do that through memory using these synchronization primitives. We also looked at OpenMP, which is a pretty simple, pretty common, pretty simple parallel programming language. Very low level. It's a simple parallel extension to C. And it's kind of pretty small extension to C. It's pretty easy to learn, but it's easy to get into trouble, as with most of C, just because it's not very high level. Okay, so we'll dive down and do more OpenMP. Just one thing was, some of the TAs said in the sections, people were... Can we turn the mic up? Is that maybe the mic's in the wrong place? Can you hear me now? Okay, that's good. Sorry, I got a bit of a cold. But the TAs said that people wanted to ask more questions in class. I try and answer. I can't answer a question unless I see your hand waving, and it's a little hard sometimes to see your arm. So if you move it from side to side, it's a little easier to spot than if it's straight up. So please ask questions. I try to answer the questions I see, but I can't see. Apparently, I'm missing some questions. So try and wave your arm, and I'll try and catch you. Okay. Any questions? Yep.
Quick question, a little bit off topic, but just to clarify, I know with ways and sets, IBM uses them interchangeably, or reverse them. So as far as this class is concerned, it's the normal way, not the IBM way all the time, correct?
Yep, IBM's is wrong. Ignore how IBM classifies ways and sets. They got it backwards. Yep. Okay. So let's talk a little about OpenMP and how we talked last time about the basic model of OpenMP is you have a sequential master thread runs for a while, and then you hit a parallel section, and all the threads, a bunch of other threads then jump in, the worker threads, who do a piece of the work. Then you synchronize again at the end of the parallel section, and you go back to running on one master thread. And that's kind of this model here, one master thread, you hit a parallel section. It turns out in OpenMP there are several different ways of executing that parallel section. The simplest one we just described, where every thread just bites off a chunk of the work and they work in parallel. You can also, in OpenMP, there's a version where you give an individual section, which is different code. Right? So the first case is every thread runs the same code, but on different data. Right? So you're running, say, matrix multiply, but you're working on a different piece of the matrix. So every processor runs the same code, just a different portion of the data set. The second example is where each thread actually runs different code. So you can, if you have sort of a mix of kinds of tasks you want to get done, you can split up the code, and so each thread will do a different piece of code. So that's described as sections. We're not going to do much of that, anything more on this in the class, just so you're aware of this is a different thing you can do in OpenMP. So give each thread a different piece of code to run inside that parallel section. And finally, something that we won't be using at all is you can also, in OpenMP, indicate that this code should just be done by one of the threads within that whole section. But we're going to focus mainly on the first one of these, where every thread runs the same code, but for some different piece of the data. And the way they find out which piece of data they should work on is each thread can find out its thread ID, and based on that, figure out what work you should be doing. Okay, so OpenMP, all the directives are given in there's several ways you interact with OpenMP. Predominantly, you add in these directives, which are pragmas. And these are preprocessor commands. And the nice thing about these is if your system doesn't really support OpenMP, it can ignore them. And then you just have a regular sequential C program. But here, if I declare this as a parallel section, all the work in the braces is going to be done. All the different threads in the parallel threads are going to pick off. They're all going to do this work in parallel. You can also annotate, there's a for keyword here. You can say pragma OpenMP for, and the immediately following for loop is the thing that's done in parallel across the threads. If it's the only, so this construct works if this is the only directive inside the parallel section. There's also a better and shorter and cleaner way of writing it, where you just say pragma OpenMP parallel for. And what that says is the immediately following for loop is the thing that should be parallelized across the threads, right? So imagine your code, you have a for loop anyway. You just add this directive in front of it, and magically that loop will then be parallelized across all the threads in the system. So the way this works is if you have a for loop, the index variable may vary. You may go across an array that has thousands of elements. You may only have 4 or 8 threads. So you have to somehow divide the loop iterations into chunks that fit on each thread. So each thread is going to pull off not just one iteration, but some run of iterations. And say, for example, you had just this simple for loop zeroing a chunk of memory. If you sort of set this, so notice this loop goes from I equals 0 up to max. So there's max iterations in that loop. If you put a pragma parallel 4 in front of this, and you only had 2 threads in the system, then the way it would work is you'd have the first half allocated to thread 0, and the second half allocated to thread 1. Okay. So the for loops have to be pretty simple, straightforward for loops for this to work with OpenMP, right? One other thing is these for loops, there's a few features you cannot do in order for it to be parallelized. So they cannot have early exits and breaks. So you cannot kind of partway through the for loop decide to exit the whole for loop construct, right? If you think about it, that would be very difficult to parallelize because say you did a break or exited in iteration 33, meanwhile one thread has started on iteration 50 and it's been going for a while, right? And it should have stopped at iteration 33. So there's these restrictions on what you can put inside the for loop in order to allow a simple pragma to parallelize it. Okay, so it can only really be relatively simple for loops that this works for. Okay. So this is sort of showing you the example again, written out with the pragma in place. So what happens when you hit this in the code, the compiler, once it sees this, will generate code that at that point will dish out the work to additional threads. So remember, most of the time there's just, in between these parallel sections, there's just a master thread running, a sequential code. It hits this loop. At that point, the other threads that have just been idling, they get assigned some subset of loop iterations to work on. They go off and do their relative piece of the for loop, and then there's a join at the end to make sure they're all done. Then you go back to running sequentially just on one thread. Now, this particular construct, remember in OpenMP, everything is shared by default. All the variables you declare, by default, all the variables see the same version of all those variables. There's only one copy in memory of all those variables. You have to declare them private if you want a unique copy per thread. Now, for the for loop, when you do add a pragma to the for loop in this way, it by default actually, in addition, makes the iteration variable I private. Okay, so if you think about it, it kind of has to be true. Each thread is going to work on a disjoint piece of that loop. Some number of iterations get allocated to each thread. They need to separately count through those iterations. So by default, it will actually privatize that loop index variable. When you do a pragma OP parallel 4, this I then becomes private by default. Right? That just saves you having to explicitly do the private I every time you parallelize a for loop, because you're always going to need that index variable to be private to each thread. Okay. So we talked a bunch about synchronization last time. What's nice about this simple kind of loop-based parallelization is there's no difficult synchronization to do. every thread is doing an independent chunk of work. You just have to wait at the end for them to come together and be done, and that's all handled by the system. So you just write the for loop, and at the end of that parallel for, everything will be back again to one sequential thread. Right? That's the implicit synchronization. Now, one thing is worth, we'll go into this a bit more depth about why you do this, but a good question to ask is, why do you divide the iterations by giving a sequential run of iterations to one thread, and then the next sequential iterations to a second thread, instead of, for example, round robbing and saying thread 0 gets iteration 0, thread 1 gets iteration 1, thread 0 gets iteration 2, thread 1 gets iteration 3, and so on. Instead of ping-ponging between the two threads iterations, why do you give each one a sequential run? Right? Why do you think you do that? Yep.
Spatial locality.
Right, spatial locality. So you want, locality is important in the memory system. We'll talk about parallel caches.
What's n in that equation?
It's the the end of the loop you're working on. Like how many iterations are there in the loop? So it'll be max in that loop up there. Like how many iterations? N is the total number of iterations. Yeah, that's not clear on the slide, but yeah, n is the number of iterations.
So isn't that maxing?
This is a general. Yeah, this is saying in general. This is what you do. This is a particular case where n is max. That's an example loop where n equals max. Okay, in general, n is the number of loop iterations, right? Okay, so the reason you give each thread a contiguous set of iterations to work on is this spatial locality, because all the data structures are going to be such that if one thread starts touching a certain point in memory and it steps to the next iteration, those are going to be neighboring words in memory, and your caches and everything else are going to work better by giving each thread a contiguous run of iterations to work on. Just some other OpenMP stuff is useful to know. Yep, question?
On the last slide, I still didn't get the second bullet point at the end. Like, it makes sense that each thread is just 0, 1, 2, and thread might be smashed in that way.
So if you have n threads, sorry, yeah, I got this wrong. This is right. Max is the number of iterations. N is the number of threads. Sorry. Yeah, my mistake. Right, so n is the number of threads. So we divide max by number of threads. So thread 0 gets the first nth. Thread 1 gets the next nth of the iterations, and so on. Sorry, that was my mistake, yeah. N is the number of threads, not the number of the loop count. Max is the number of iterations in that loop. Okay, so get time is another OpenMP command that's just there to help you count the time. As you do in the project and trying to performance tune, you're going to be very interested in how fast is my program running, right? And W time, it's called W time because it's measuring wall clock time, i.e. real time, the real world, how many seconds have elapsed. And the way that the timer works, it just runs continuously. You get a value that comes back in seconds, but it's seconds since some arbitrary point in the past. So when you're timing a chunk of code, you need to grab a time at the beginning, grab a time at the end, take the difference, and that tells you how much time elapsed between the two calls. All right, so you always measure before and after and subtract to find out how many seconds it took to run some piece of code. So this is how you do performance measurement and drive your performance optimizations that way. So this is just a standard call in the OpenMP library. So just to give you some more code examples, this is matrix multiply parallelized in OpenMP, a very simple way of parallelizing matrix multiply. So if you ignore this line of code here, right, all you have are the 3 nested loops for doing a matrix multiply, right? And so the matrix multiply we're calculating is, C equals A times B, where those are matrices. And so for each row in A and column in B, you do a dot product between those two, and that gives you the value in the C matrix, right? So it's just textbook matrix multiply. And so this inner loop is just running down one row and one column of the input matrices and calculating the result in the output matrix. And then the outer two loops just, traverse all the entries in the output matrix to calculate the result, right? So this is m dimension, n dimension, p dimension for these three matrices. So notice in here you have a temp variable, which is just where you accumulate the sum. And this inner loop is just doing a dot product. It's reading a value from A, a value from B, multiplying them together, and adding them into the sum, okay? And this is just using point arithmetic to get at the right element in those two-dimensional matrices. Okay, so if you ignore this, and this just writes the result back out to the C matrix, okay? If you ignore this line, then this would just be a sequential C program that did a matrix multiply, okay? But when you add this pragma in front of the outer for loop, you tell OpenMP, parallelize this for loop, make temp and J and K private. I is actually should be private by default, but it's okay to add it in there. And then what this will do is this outer for loop is the loop that was going to be divided across all the threads you have. So each thread will get a separate set of that outer loop to do. And then once it starts running, you're going to be computing results in parallel across those multiple threads. Yep. K is the index variable in this inner loop. So as you're stepping through the dot product, so the outer two loops are basically, you have a 2D matrix, and the outer two loops are stepping across the entries in the result matrix. So one loop is going this way, one loop is going down each row you do all the columns, next row you do all the columns. That's the two outer loops. Then the inner loop is at each point, you need to step down the input matrices to do the dot product. And you sort of multiply and add those values together to calculate that one result in the output matrix. So that's the inner loop, right? So you see that's, so you set the sum to 0, you do the multiply and accumulate here, and this just does the inner dot product that calculates one result in the output matrix. And then the outer two loops are just traversing all the elements in the output matrix. Okay. Yep. So the question is, we've only seen parallelism for for loops. Does a parallelism exist in other kinds of loops, like while loops? So it's a good question. While loops are actually very difficult to parallelize because a while loop is something you do until some condition occurs in the code, and then you drop out of the loop. And so you can't just parallelize it by doing loop iteration. Like I said before, if you did, that's the reason why you cannot have breaks or exits from the loop, because the reality is that the loop iterations are not independent. I need to know whether the previous iteration's finished before I know whether I should do this one, if there's a while loop. And so they're not actually independent. And so to do things in parallel, you need that to be, the things have to be independent from each other. If they depend on each other, then one thing has to kind of wait for a result from the previous one. In this case, you're waiting to know whether you should go ahead or compute a result at all if it's a while loop. Yep.
So then you mentioned the command break was significant. So what happens if you have that in
I think it's illegal. It just says you cannot do that. It's an error to include that in the code. Right, so that was the so you're not allowed to have any of these things in the loop because then it's not clear that these things are independent. Another way of thinking about this is when we did the process of pipelining, remember we talked about how instructions go down the pipeline, but they all depend on each other. So while loop is kind of like a control hazard. I don't know if I'm supposed to do the next iteration until I've completed the last one. Here in the simple for loops, you know that you kind of know with the matrix multiply, I'm going to calculate all of these individual results, regardless of what happens in the other places. So it's easy to parallelize. Yep, question?
What about this branching? Is there a way to sort of guess that you continue and plus, or is that not?
Yeah, so that's actually, the question is, can you do it like with branching? Can you just guess and then keep going? Yes. So a more advanced way of parallelizing, you do some speculative parallelization. I'll guess that I'm actually going to complete these iterations. I'll calculate the result into a temporary buffer. If I then find out the while loop continued past this point, I can just write the results into the actual location Yes, so you can parallelize that way. That's a speculative parallelization. Yeah, that would work. But you cannot do that straightforwardly in standard OpenMP. You'd have to write that yourself. More handwrite that yourself, that kind of parallelization. Okay. Right, so now we've added this statement in, and that sequential loop, what was a sequential loop now becomes a parallel loop, and the OpenMP system will then just break up that outer loop across the threads, and you should get some speed up. Oh, and notice here, this is timing this loop, so we have you record the start time by doing get W time here, and then the total run time is just the current time minus the start time, right? And that's how long you know this piece of code took to run. Right. So getting back to why you want to spread the loop iterations the way we did, if you think about these inner loops, there's going to be a lot of locality as you step through this loop on one thread, or these iterations on one thread. You're going to stay in the same region of memory and get more locality. So that's why you want to divide things up that way. So this is a really, really simple matrix multiply code. And if you're really doing a high-performance implementation, which you'll be actually doing as part of the projects, there's a whole lot more optimizations you can do to improve the performance of this. The simple thing is just change the compiler flag, so you force the compiler to work harder and find more optimizations. Another thing I think you've covered in sections is cache blocking, so changing the order of which you access memory to increase the temporal locality of the matrix multiply. So you go to memory less often. That's a good thing to do. And also, finally, we covered in class and section using the SIMD instructions. So, with these simple parallel loops like this, you can use the SIMD extensions to do multiple operations in one instruction, right? That's another way of getting a big improvement in performance. So you'll be exploring a lot of these in the project as you get to do that. This was just a simple example to show you the OpenMP syntax. Okay, let's dive down a bit into the hardware. What does a parallel system look like? Well, this was our simple model of the real computer. You have a processor here talking to memory. So the processor has a control unit in the data path, the program counter registers, and it's stepping through, fetching and executing code and reading and writing from memory. So a simple way to build a multiprocessor, you just add a second processor, right? So second processor does the same thing on it's a different place in the code. It has its own program counter, works on its own set of data, and these guys just communicate through the memory system. Now, if the memory system is a bottleneck even when you have only one processor, as you start adding more processors, the memory system's going to become increasingly the bottleneck. So when you're building multiprocessor systems, you really want to add caches to help isolate the processors from the speed of the main memory. So you're going to use these caches in a multiprocessor system also, and it's even more important there because you have all these different processors now banging on the same main memory. And so each unique processor core is going to have its own cache, right? And so only when you miss in the cache, you have to go to the shared memory, right? And so this is kind of the structure you end up with, where I have separate processors, each with their own private cache, all talking to the shared memory over some set of wires, some interconnection network that connects all the caches to that main memory system, right? A very common structure here is what's called a bus, and a bus is just a collection of wires that allows one at a time. So one of these caches at a time can communicate with the memory system and back again. Most of the time, you hope the processor is just working out of the cache and just occasionally gets a miss and has to talk to the memory. If two of them miss at the same time, the bus has to arbitrate and decide which one gets to go ahead first, and then the other one waits, and the second one gets to go ahead to access the shared memory. Also, this is how, when you build a multiprocessor and you have I/O devices, which we'll cover in the next couple of weeks, the processor needs to talk to the I/O devices, and all of the processors you want to talk to the I/O devices. So they also go over the shared bus to get to I/O. Things like the network connection or the disk drives will be hanging off this connection here. So now when you have caches, you're going to hit this problem of keeping those copies coherent. So if each processor has its own cache, remember that a cache keeps a copy of what's in main memory. And if, let's take this example with two processors, 1 and 2, just read this memory at location 1000, and it has the value 20 right now. Okay, so this processor reads location 1000. It's not in the cache, so it gets a cache miss. It goes over the network, goes to memory, asks the memory for what's the value in location 1000. The value is 20 right now. So you take that value, you return it back to the cache, and you keep it in the cache. Right? So you had a cache miss, you got the value for memory, you place it in the cache. So now you have a copy of that address in processor 1's cache. Okay, and now processor 2 also accesses location 1000. So it looks in the cache, gets a miss, goes to memory because it was a miss. Asks for the value is 20. You send value 20 back to that processor, and now it has that location memory cached as well, right? So both of them in their own caches have their own local copy of memory address 1000, right? And they both agree the value is 20, and 20 is what the value is in main memory. Okay. Now what happens when processor 0 comes along and writes 40 to location 1000, right? So what happened to the animations? I don't know. They disappeared. Anyway, this guy writes location 1000 with the value 40 and updates memory with the value 40. Let's pretend this is a write-through cache. So what's the problem? Yep. Right, the other caches have the old value. So think about what would happen if they all tried to read location 1000 right now. So this processor would see 40, this processor would see 20, and this processor would see 20. Because they'd just be looking at that value in the cache. They'd all think, oh, great, I got a cache hit. I'll read that value, but the value here is stale, right? It has the old value in location 1000. Yep. Okay, I think what you're getting at is that the processes are communicating, and if you want things to be parallel, they shouldn't be reading and writing each other's data. I think that's what you're... Right, so if you think about within that parallel section, that might be true. Say they all work on independent pieces of the matrix, but then at the end of the parallel section, you have a join and you're back to just the master thread running. Now the master thread may read a value that one of the worker threads produced. In that case, it's after you know the loop is finished, I'm ending the parallel section, and at that point, I want to read that value. And so I then have to still worry about this staleness, right? If all the processors only ever touch their own independent disjoint sets of addresses, you wouldn't need to worry about this problem. But in practice, they will share values in the same memory. Maybe not within one parallel section, but in the serial section or across to the next parallel section. So you do have to worry about these guys reading it. Okay, so the problem we have here is that the caches are keeping local copies, and those local copies can get stale as values get updated by other processes. And so the solution that's adopted in hardware is, it turns out actually this is incredibly difficult to do in software. Like the usual response from hardware designer is, oh, that's unfortunate, let software deal with it. Go ahead and it's your responsibility. My job is to make things go fast. Right, but the reality is it's almost impossible for software to deal with this, although many people have tried. And in practice, systems today, it's the hardware that actually manages this coherence and makes sure that every processor sees the recent writes that are made to any memory location, so they never see a stale value in the caches. And the technique that we use here is a cache coherence protocol. We're only going to sort of touch upon this today. If you want to find out more about coherence protocols, you should take CS 152. We'll cover them in a lot of detail. But the general strategy is when a processor writes a memory location, it goes across the interconnect bus and tells all the other caches, hey, I'm going to write this address. If you have a copy, make it invalid. Okay, and then it can update the value in main memory, and if one of the other processors tries to read that location, they'll then get a miss because the line will be invalid, forcing them to go out to main memory and getting the new version, the new fresh version, out from the main memory. Okay, so that's the general strategy. So this simple technique is called snooping. Yep. Sorry, I couldn't hear that. Okay, it's a good question. I'll answer that in the next slide. Right, the question was, why can't they just send a new value to the other caches? That's a reasonable thing to try. So the main technique that current systems use, especially smaller scale systems with just a few processors, is called snooping. And the idea here is that, all those caches are connected to the same set of wires going to main memory. And the idea is the other side of all the caches is continually monitoring that bus to see which writes are the other processors doing. And if you see a write to a location that's in your cache, then you will validate the value in your cache. Okay, so now we have this scenario where this guy's read 1,000, has the value 20, and this guy's going to write to location 1,000. Now the idea is this guy gets a cache miss. I don't have location 1,000. I'm going to write to it. Broadcasts 1,000 on the interconnection network because it's going to the memory to get the location. These other caches are looking at these values flying by. And then when they see a match, like this address flying by here matches, it's kind of a cache hit from the other side. So the memory system looks into the cache and says, do you have this address? And if you do have that address, you need to invalidate it. Okay, so then this value is no longer in these caches. And then this guy writes to memory. And now what will happen when these guys try and read that location, they're going to get a miss, go to memory, and get the new version. Right? Okay, so that's the standard way people do. And this is called a write-invalidate protocol. So writes invalidate the versions in other caches. So the question at the back was, why not send a value and have the other caches be updated with a new value? Right? And so that's also possible. It's called a write-update protocol. So in that case, this guy, when these get a cache hit, you would read this value and write it into the caches. The main reason people don't do write updates is quite often the other caches don't actually care about that value anymore, for one thing. And so you update the value in this cache, well, I'm not interested in location 1,000 anymore anyway. So, and doing the write update usually involves more traffic across this bus than just sending the address. Yep.
Is there like no advantage to like, let's say having all the processors like share their own caches with each other? Like the processor want to process to test them, like main memory, why would they want to like look in it like later?
Okay, so the question is, why not just have these guys share these caches? So remember, we're working in a physical world, right? And so all the circuits have to fit in a certain space, and signals take time to propagate. So if you were to allow each processor to look in everybody else's caches, that would slow down every access to the cache. So as well as providing, you're exploiting locality in the address stream by building these small caches around the processor. Because they're physically small, they're also fast in terms of nanoseconds to access. And so what you don't want to have to do is wait every time you access the cache to go look in other people's caches also. So the whole point of having the small, fast memory was I only have to look in here, and hopefully it's in here. I don't have to go outside this little domain to find that data. And so if I made every search in the cache also look elsewhere, it would slow the cycle time down of the processor by doing those other searches. In effect, what happens with the caching, the multiprocessor caching, is I look in my own cache first. And in this simple example, I just have one level of cache, and I go straight to the memory system, which, because it's snooping, is looking at everybody else's cache. And actually, one thing that happens is, say I get a miss here, and I have a write-back system, and the line is dirty in the cache. That means the memory doesn't have the right value. Somebody else's cache has the most recent value. And in effect, I will read it from that cache, sometimes directly. Sometimes I will force the other cache to write back that value to main memory, then invalidate it, then read it from main memory. Just to go one level further, most systems these days have multiple levels of caches, and usually the last level of cache is shared between all the cores on the chip. So before you go out to DRAM off chip, the last level of cache is shared, and in there you'll find, if somebody else brought the data on chip, you'll find it in that last level of cache. But you always have your private caches first, just to make sure the processor can run as fast as possible. Okay. Let's see if people got bored hacking the clickers last time. Okay. Let's give you a couple minutes to think through these questions. Okay, let's take a look. Okay, there's a few alternative choices there. People are pondering. Let's give you a couple of minutes to talk with your neighbors. Okay, so Everybody's coalesced around that answer. That is the correct answer. Let's just go down through these, though. Help explain a bit more about caches. So does using write-through remove the need for cache coherence? Well, actually, the example we gave here, was actually using a write-through cache, right? It was write to memory. Oops. When you do write-through, you update memory. It doesn't stop the caches being incoherent unless you do something about it, right? So write-through caches alone won't help you. Every processor store instruction must check contents of other caches. Well, if it's in your cache and it's dirty, if you've already done a store and brought it into your cache and you modified it, when you do another store to that same line, you know that nobody else has that line, right? Because they could only have that line if they had a copy of it, and that must be a clean copy of it, right? If you're going to write a line, only one process at a time can write the line, because when you go to write it, you send it on the bus, you invalidate all the other copies. So only one processor at a time has a writable copy, right? And so if you find it in your cache and it's dirty, you must be the only one with that line. And so you can just go ahead and store without even telling anybody on the bus, because you know that nobody else has that line, right? So not every processor store instruction has to go out and check all the caches. And so D, skipping to the last one that's incorrect, only one processor can cache any memory location at a time. We already saw that if you just multiple processors are reading, if they're all reading the same location, that's fine. You can have multiple processors with a readable copy of the same location. That's a good thing, especially for things like instructions. Remember, you have instruction caches too, right? You want all the processors to have the same instructions cached in their own private instruction cache. So it's definitely true that every processor can have a copy of a given memory location, but the only caveat is only one at a time can have a writable copy that it can actually update, right? But you can have read copies in multiple places. So yeah, and the result of this is that most of the time, most of the processor load and store instructions are just going to be satisfied by your local private caches. And that's the goal, to kind of offload the main memory system from the memory requests of all these different cores, sort of banging away on the same the memory setup. Okay. Let's do a little bit of administrivia. Not much to say. You have a midterm on Thursday. So it covers everything up to the March 31st lecture. And you're allowed 2 cheat sheets. And you will be allowed 3 cheat sheets for the final. Standard 8.5 by 11. Okay. And that'll be in here, the same format as we did for the first midterm. Right. That'll just be in class. Any questions about the midterm? It's coming up. What are the questions? No. Yep. You have to wear the SIMD stuff. Yeah, that lecture was the SIMD lecture, I believe. Yep.
What's the definition of 2 sheets? Is that like 4 sides?
We had 1 sheet in the first midterm. Now you get 2 sheets. The same definition, right? 2 of those. Actually, the cheat sheets, most of you should probably realize the real reason to do cheat sheets isn't to use in the exam. It's to study to put the stuff on the cheat sheet. How many of you actually looked at the cheat sheet during the last midterm and found anything useful on it? Wow. Okay. Interesting. Now, we recommend doing cheat sheets not because you can use an exam, just to help you study, and goes through your head and out onto paper once. There's some chance it's stuck on the way through. Okay. All right. Any other questions about the midterm or anything else? Okay. Okay. Let's just move on. So, question? Okay, that might come up as we walk through this next few slides. So the way that cache coherence scheme works is it works in units of cache blocks, cache lines, right? So remember that the caches, usually you use multi-word cache lines these days, and that's to take advantage of spatial locality. and also to save on tag cost, right? You have one tag for multiple words of data. So most caches are multi-word cache lines, and for example, on the x86, the Intel processor, 64 bytes is the standard cache line size. So the coherency schemes don't actually work at the level of individual words, they work at the level of whole cache lines. So you're tracking, remember there's only one tag for the whole cache line, and so when you're doing the snooping and other things on the cache, you're actually sending around the address of the block, not of the individual word within the cache line. So when I get a cache miss, I fetch a whole block. It's that address that I put on the bus and snoop in the other caches. So you don't have that fine granularity of looking at every word in the line, just at the whole line. So here's an example here. I have two processors, both with private caches, and with a 32-byte data block, right? So here's the data addresses of this cache block. So you have one tag, address 4000, but then you have 4000, 4004, these multiple 32-bit words in this one data block. So now let's imagine this processor is running a program, a thread, some task, that's accessing this variable at location 4000. This processor is running a different task that's accessing memory at location 4012. So those are two different words in memory, but they live on the same cache line, right? They just happen to map into the same cache line. Now, the way the memory system works is it moves things around in units of cache lines. So now the problem you'll see is that if they're both reading and writing these two variables, they're independent variables. They're not touching the same location in memory. They're just touching the same line, cache line, right? The coherency is tracked at that granularity. So what's going to happen if this guy reads and writes and this guy reads and writes these locations? What's going to be happening in the system? Can they both have a copy of that line and read and write from it without going over the interconnection bus? What's going to happen? Yep. Right, so you can have a lot of misses because even though they're accessing different words, they're accessing the same cache line. So say one of them doesn't have the line in its cache and tries to do a write to that variable. It's going to get a miss, going to go on the bus with the cache line address. That's going to be snooped by the other cache. It's going to see, oh, somebody's writing this cache line. So I have to evict my line. If it's dirty, write it back. Then the first guy will pull that line into its cache, update the variable. The other processor then come back to running and touch its variable, which is a different location, the same cache line. And now I'll find, oh, I got a cache miss. I have to do the transaction on the bus. And so this line's going to ping-pong back and forth between those two caches. Because the thing we preserve is that only one cache at a time can have a writable copy, right? But they're both writing to this line, just at different locations in the line. So as a programmer, this is really frustrating because you think these are independent variables. You don't think these processes are communicating at all. But it turns out you get a lot of communication traffic in your system. Your system's going to run really slowly. And so this is called false sharing, right? You think the traffic pattern in the system, if you put an analyzer on the bus and watch what was happening, you think these two processes were communicating a lot. But they're not. They just happen to be touching two different variables on the same line. And so this is really false sharing. There's not really any real communication going on. It's just an artifact of the coarse grain at which we track the coherence information in the system. So how do you prevent that from happening? Only load the specific byte, but they're only actually touching that specific few bytes. One solution is you could go back to having single word cache lines. That would avoid the false sharing problem, right? But the problem then is I remove the benefits I had from multi-word cache lines, lower cost in tags and spatial locality. couldn't really hear that. So. Do something with the offset. So you may have a more complex coherence protocol that kind of knew about the subwords. Possibly. What's the simple, like we're hardware guys, what's the simple thing you could ask the software folks to do? You know, if it hurts, don't do that, right? So how would in software you ensure this happen less often? Any ideas? Yep. Right. So the real trick is, allocate your data structures in memory such that if, multiple processors are accessing stuff, have them be on different cache lines. So move things apart in memory that different processors will access. And so this gets back to why in OpenMP, when you allocate loop iterations to threads, you put contiguous loop iterations on the same thread, because that means the chance of, say you're stepping through a matrix, the places where both of two threads may access different parts of the same line are going to go down, because it's just be at the boundaries between those chunks and not all the way in between. The worst case would actually be if you went round robin and gave thread 0, element 0, thread 1, element 1, thread 2, element 2. If you did that, you get terrible false sharing. So you kind of allocate as much big chunks as possible to one thread, and so you only have to worry about false sharing at the edges when you go from one thread to another in the data structure. So try and allocate your data structures in a way you don't get this false sharing. So this is actually one of the big, this is actually quite a big and real problem in real code, and it's often a cause of performance problems. People don't understand that, I didn't realize I was actually touching the same variable, the same cache line through two different variables and two different threads, and that's where all my performance is going. So it's something very much to be aware of. Okay, let's go back. I just want to talk about the state of the cache lines, the question over here about how do you manage writes and dirty bits. So when you have a cache system like this, sorry, question?
So you're saying that the approach to avoid false sharing is through software?
Yeah, the main way you avoid false sharing is through software.
So it's up to the software programmer to know what the size of, the specifics of their hardware so they can account.
Yeah, it's a good question. So, you might think, well, that means the software has to know how big the cache lines are, for example. At some level of detail, possibly, but usually it's good enough to, if you understand that phenomenon, to know that, well, if I spread things apart, for example, with the way OpenMP gives a lot of iterations to one thread and then the next set to a different thread, you don't actually need to know the cache line size to know that this will usually help, regardless of the cache line size. So there's a lot of techniques that, independent of the cache line size, will be better or worse for false sharing. If you're a very highly optimizing thing, then maybe yes, you need to know what's the cache size, and you allocate data structures so that you'll pad them out so they'll go to the next 64-byte cache line. If you know two threads will be allocating it, yeah. So if you're really performance programming, you will need to know the cache line size. But a lot of the tricks don't, you'll know they'll generally be better, regardless of the cache line size. So that's a lot of what people do. So in this cache coherence system, when we question. The question is, do you want these caches to be the same size, or do you sometimes want to be different sizes? So usually if they're the same kind of processor, the caches are usually the same size. So, conventional multiprocessor, like you see on servers or in your phones, like in your iPhone, the two cores in there, they both have the same cache sizes. But if increasingly people are building systems with different kinds of processors on the same memory system, so your GPU, the graphics processing unit, and the CPU will have different size caches, but they'll be talking to the same memory system. So they'll be optimized for each kind of processing unit you have. Right. So in this multiprocessing system, this cache coherence hardware has to keep track of the state of all the lines in the caches, right? So we already talked about how in a single cache, in a uniprocessor, you have a valid bit that indicates if this line is present or not, and also a dirty bit to indicate have I modified it since I brought it into the cache, right? So when you evict it, you look at the dirty bit to see whether you need to write it back or not. In the multiprocessor case, you can reuse those 2 bits to track the state of the line. They mean kind of the same thing. So we already talked about a write invalidates the lines in the other caches. So now the invalid bit is not only being used after power on, it's being used during normal operation to indicate that somebody else has invalidated your line, right? So now you're using the valid bit as you're running code. The dirty bit you can also use to indicate that this line is dirty in this cache. That also tells you that no other cache can have a copy of that line, right? Because any transaction that will lead to that line being dirty must have invalidated the copy in all the other caches. That's how you know that this cache can straight ahead go and write that line. Now, as you go through, I think in section we're going to cover some of the other states you can have. It turns out cache coherence protocols are very widely studied, intensively studied. There's many schemes out there. And one of the things people do is add more and more different states a cache line can be in. For example, you can bring a line into a cache clean, as in it's the same as in memory, but you know that you're the only cache that has a copy of that line, and that would be an exclusive state. So I have the line, it's exclusive to me, but I haven't modified it yet. The nice thing about that state is I can immediately dirty that line in the cache without talking to the other caches in the system. Then it becomes dirty and also exclusive. So getting back to the question, basically there's a couple of state bits on each cache line. Just as in a sequential cache you have invalid and dirty, the multiprocessor you have those 2 bits as well. So sometimes they're used to encode a few more states that help you avoid going out to the bus when you don't need to. Yep.
So every store does have to communicate with all the other caches, meaning that it has to invalidate that to validate?
No. So if this processor, let's go step this through. This guy does a write here, invalidates the other copies. At this point, it's now present in this cache, right? And it's dirty, say. This processor, if it does a second store, it sees the line is dirty. It knows there's no reason to go on the bus. I'm the only one with a copy of line 1000. I don't have to go to the bus to invalidate anybody else. I've already done that. And I know that because the line is dirty in my cache. If it's dirty in my cache, I'm the only one who can write to it right now. If somebody else tries to write to it, they're going to have to invalidate this line, flush it out to memory, read it in again. It'll be invalid here. But I can actually, if I know the line's in my cache and I know it's dirty, I know I'm the only one who has a copy. It's okay for me to write it in place without going on the bus. Okay? Yep.
So if you were using a write back cache and you're engrossed in that cache, and now that bit is missing and all other caches are invalidated, if those other caches wanted to access that memory, how would they?
Right, so if now you're in this scenario where say this is dirty in this line, in this cache, and these guys don't have a copy, then this guy wants to read it, he'll get a miss, he'll go on the bus, this cache will snoop that request, and then that will cause this dirty line to be flushed out to memory, and the copy sent to this cache. And then this cache will have it clean, because it'll match what's in main memory. And this guy will be invalid now. And there's lots of variants where, for example, instead of making this invalid, you can make this guy clean because it matches memory, and this one can be what we call downgraded from dirty to clean. So now he retains his copy, but it's a clean copy. So actually, if you have a copy that's not dirty and you try to write to it, you know you have to go ask for permission to invalidate all the other copies, right? So I'll replay that again. So this guy has it dirty, nobody else has the line. This guy wants it, issues a read request. This guy snoops it and says, oh, I have that location, I have it dirty. That means I have to write it back. Let's say it writes it back and resets the dirty bit to clean, gives this guy a clean copy. Now they both have a clean copy of that line, right? But now if one of them wants to write it again, they'll see, oh, I have to actually go on the bus and request and validate the other copy. And so the goal is only one cache at a time can have a writable version of, that's the invariant you have to maintain for the system to work.
So then if, say, the middle processor decides to write at a completely different value, how does it know that the other two don't have a copy?
Okay, so the question is now if these two have a clean copy, this guy wants to write a different value, what happens? Well, he'll get a miss because he doesn't have a copy. He'll go on the bus, both these caches will snoop that request, invalidate their copies. This guy will get the version from memory. He'll then get it, he'll write it and make it dirty. So then only that middle cache will have the value dirty with a new state, with a new value in there, right? And the other two will be invalidated. So the fact that every time you miss, you have to go in the bus and tell everybody else, and they'll snoop, and they'll change their caches accordingly. Right? So there's, you know, we're trying to do the very simplest cache coherence schemes. There are many, many schemes, and you should take 152 if you want to learn more about all the different optimizations people have done for this. We're trying to give you the basic idea of there are caches, they have to be kept coherent, and when you write programs, parallel programs, you're going to be hit with these issues of false sharing. Okay. Okay, so one thing I also want to do is review, there were some questions about the 3 C's, and some, unfortunately, previous iterations of this class got this stuff wrong apparently, and there's a lot of incorrect definitions floating around. So let's go through the 3 C's first, because I want to talk about the 4th C after we've done the 3 C's. So the 3 C's, a compulsory miss. So the first thing to understand is, what are the 3 C's about? They're about understanding misses that actually have happened. So when you look at a program and you run it, as an architect, you want to understand, why did those misses happen? And this is trying to assign blame for why did a given miss occur, right? And there's this nice categorization into these 3 categories that's helpful to understand, you know, if you could improve it and what you should do to improve the miss rate. But remember, this is all about misses that occurred, why did they occur? So if you got a miss and it was to an address that you hadn't seen before, that's a cold start miss or a compulsory miss, right? You hadn't seen that address before, that's why you got that miss, right? So that's a compulsory miss. Capacity misses, this is when there's no way your cache is big enough to have avoided that miss, right? And the tricky thing with this is the actual definition is the cache cannot contain all the blocks accessed by the program, even if you had a perfect replacement policy in a fully associative cache, right? So even if the cache was could look into the future and figure out the next billion requests you're going to make, and then kicked out exactly the right entries to improve your miss rate, you're still going to get a miss because there just isn't enough space to hold all the data you need, right? So so I'm doing these in an order of, first you look and see, is this the first time was that miss to an address that's the first time I've seen that address? If so, that must be a compulsory miss. So you're done with that missed request. No need to think about it any further. If it's the first time I've seen that address and it's a miss, it's a compulsory miss. Now you come to the next kind of miss, which is with a finite size cache, with a perfect replacement policy and fully associative, so there's no restriction on what lines I keep. There's only a restriction on how many I keep. And you still get a miss. That's a capacity miss, right? Basically, if there's nothing I could have done with that finite size cache, there's no better way of laying out the blocks I keep, I would still get a miss. Then that's a capacity miss, all right? And the final category is things that occur basically because in a finite size cache, it does worse than there's some misses that occur because you don't have a perfect replacement policy in a fully associative cache, right? And those come about because you have restricted associativity, maybe only 2-way, 4-way, 8-way, or whatever, some finite associativity, or because there's something wrong in your replacement policy, right? Those 2 things are what causes a conflict miss. All right, question?
So if you have a capacity miss, is it fair to say that your caches must be full currently?
Yeah. Yep. Sorry, say again?
In the midterm review slide, the example of determining which miss it was, the last example, or the last miss was a capacity miss because you replaced the 3rd block, even though the 4th block is still empty.
That's actually wrong. It's a conflict miss. So that's what I'm saying. I think some of the material is, we should fix this that's actually incorrect. So now one of the difficulties with this categorization is you cannot, unfortunately, you cannot just add a little widget on your hardware that tells you as the miss happens which one it was. Right? To understand it, you actually have to run the program in a simulator and model things. And the thing to realize about this is useful for architects understanding how to design systems. It's not really, it doesn't help a user trying to tune a program because you cannot, at runtime, tell the user what kind of miss they got, right? So this next slide might help explain how we use this. It might give you a better understanding. What do we mean by these kinds of misses? So imagine now you're going to use a cache simulator. What's a cache simulator? It's something that you run the program, get the addresses it accesses, and feed them in the simulator to tell you whether the cache would have missed or not. Your question? If your cache is direct mapped, it'll have all three kinds of misses, depending on the circumstances. So the direct map cache where you only have one row, you can still have all three kinds of misses. Right. Okay, so you definitely have compulsory misses, right? If I haven't seen the address before, that must have been a compulsory miss. Okay. The capacity miss, if you only have one line in your cache, the line's not long enough. You could say that, but in this case, they're about the same, capacity and conflict misses. But you're still going to have compulsory misses as opposed to, most of the misses will be capacity misses. There won't be any conflict misses, actually. Strictly speaking, there won't be any conflict misses. Right. Okay. So the way you get these numbers, how you categorize this stuff is you actually have to run the program, see the address trace that comes out, all the requests it makes, feed into a simulator, and this is not a regular simulator. It's something that's designed to tell you how to categorize these misses. And actually, this was developed here at Berkeley by a grad student about 30 years ago. So. No, that's not, okay. Let me go through how you actually calculate it, then I'll take questions on what it means, right? So this is actually how you get, this is the strict definition of what it means. For all of you who are panicking about how do I do this on the midterm, just step back and think, okay, is this related to, I can't fit all the data in the cache? It's probably a capacity miss. I get conflicts because of how I'm fitting the data, but there's some other space I could have used if the cache was more associative, then it's a conflict miss, right? That's the intuitive way of thinking about it. I just want to formally tell you what it really is so people who are interested actually understand it and hopefully help their peers understand the material. Okay. So compulsory misses. Build a cache simulator where you have an infinitely big cache. Run your addresses through it. Every time you see an address, put it in the cache and record it as being a compulsory miss, right? So every address you see, if it's already in the cache, that can't be a compulsory miss, right? So you run your whole address trace through. That way you can tag certain of the accesses as causing a compulsory miss, right? That's the easiest one to see. So all those misses you don't have to worry about anymore, right? You've categorized those as compulsory misses. To figure out which of the remaining misses you want to categorize as capacity misses, you build a finite size cache that implements optimal replacement, right? So this is a really intelligent cache that looks at the addresses so far and actually looks into the future. You actually have to look into the future to figure out the optimal replacement policy. So this cache simulator actually looks at not just your accesses up so far, it looks at all the accesses in the future as well, figures out what should I replace from the cache to give me the optimal replacement, right? So this gets rid of any concern about do I have the right replacement policies, LRU, is it whatever. LRU is just an approximation of the right thing to do. When you want to figure out if it's a capacity miss, you build an omnipresent cache that knows what's coming and replaces the thing that's going to be accessed furthest in the future. It turns out that's the actual optimal replacement policy. So this simulation then, by doing this optimal replacement policy online, can tell you, strictly speaking, no matter what you did, no matter what kind of cache replacement policy you did, the cache is just not big enough to hold these requests and you'll get a miss. So that's a capacity miss. So now those misses you tag as capacity misses, and you're done with those. Everything that's left is a conflict miss, right? So that's basically how you would actually, for a given program with a given set of input data running on some system, you can figure out what the which are capacity misses, which are compulsory misses, which are conflict misses. That's strictly speaking how you do this. This is the correct definition. Unfortunately, for some reason, there was some confusion in the previous slides about previous versions of the course about replacement affecting capacity. I didn't understand that at all. So there shouldn't just be there. So this comment about whether you're replacing or not, that's got nothing to do with it. It's whether if you have the optimal replacement policy, the given size cache, and you still get misses, your cache is not big enough is the problem, right? No matter what you could have done with the better associativity or better replacement policy, cache is just not big enough. Conflict misses are, where two things map to the same place, and there is space you could have used else in the cache, you just couldn't. Yep.
Do you have to check in this order, or is it possible? I know, like in your session, they have you check conflict
Yeah.
first.
Right. This is strictly speaking. If you built a simulator, this is the way you would actually do it. Right. If you have,
Replacement is hard to know what that is.
right. That's why I'm trying to give you this is the real truth. Right. Then versions of this have been given in the course simplified. I just wanted to clear up by giving you this is actually the ground truth. You can simplify this, and they try to do that in the discussion section. But you cannot tell whether it's a capacity miss unless you implement an optimal replacement policy.
So with the optimal replacement policy, what is impossible with that and have the capacity even though the cache is not fully it's like
No, because it won't be a miss. You'll get a compulsory miss if you haven't seen it before. But if you've seen it before,
but after the long time.
if you've seen it before and the cache is not full, it's still in the cache. Right? If how could it not be in the cache if the cache is not full and you've seen it before?
But say the following members that replace the same one, even though
You have an optimal replacement policy and fully associative cache. Right, so that's the point. If when you run the capacity simulation, if your cache is not full and you've seen the line before, it must still be in the cache. Right? So you cannot get a miss then. Okay, sorry this is so complicated, but this was a PhD thesis, so, all right, and so that's, using that simulator is how, the grad student who's now Professor Mark Hill at Wisconsin, that's how he generated this kind of graph, right? So he could actually analyze code and tell you what was causing the misses. Right, that's how he did this analysis. That's how he got these numbers out. Now, the good news is there's not just 3, there's 4 C's of cache misses, right? And the 4th one is called a coherence miss or a communication miss. I actually prefer communication miss. And it's misses caused by coherence traffic with other processes. So what's interesting when you start writing parallel programs, these can actually be the dominant kind. So false sharing is an example of misses that are caused by coherence traffic, right? They're communication misses. You know, it's kind of false communication, right? So if you think about it, that invalidation that's happening on the Snoopy buses, that's going to cause misses that are nothing to do with compulsory capacity conflict. They're to do with communication between the processes. So that's his 4th category of misses. Okay. So in case some of you have forgotten, here's pi. Just as a break, there you go. No, so the last part of the class was actually just going to go through an OpenMP program to calculate pi. But I think maybe I want to stop. I want to take some more questions on caches. I think this is probably more important than the OpenMP example. Yep.
So if you're just doing one pass through an array, every miss would be in order. Every miss would be a compulsory miss, right? Because we're having your
So let's. The question here is: say I was just stepping through an array in order once. Every access to that array would be a compulsory miss. Not quite, because you may have a multi-word cache line. So the important thing about those misclassifications, of the misses you get, what kind were they? Right, so if I access the first element on a cache line, I get a compulsory miss, in this case. I bring the line in, I may get hits, because the line is longer than one word. right? So those subsequent accesses aren't compulsory misses because I had a long word line. Now, when I get to the first word of the next line, that will be a compulsory miss.
Well, I meant like all misses would be compulsory.
Right, that's a better, I was just trying to make that distinction, right? So all misses will be compulsory misses, but not all accesses will be compulsory misses. Okay, question?
So let's say you have a cache with only 2 lines, and there are 2 different sets, right? So all accesses, or all memory accesses map to like either one of the sets. Let's say you do 3 lookups, and they all map to the same line, but they're all misses. So the first one's going to be compulsory, right? The second one is going to be conflict.
Well, that'll be a compulsory miss if you haven't seen it before.
Okay, so that's like the third one. That's the one I'm actually interested in.
So-
Because
so-
I never ever
Say you're in steady state looping over those 3 addresses. So ignoring the compulsory misses. I think that's the example you want to give. So I've seen all 3 addresses. I'm in a loop. I always touch these 3 variables, and they all map to the same line. That's the example I think you...
So if you only have 2 lines and you have 3 different things, will the third one, if the miss, will it always be a capacity miss because you only have 2 lines and you want to do cluster?
Right. So I think it's a good example to work through. So I have 3 lines total in my cache. Sorry, 2 lines total in my cache. I have 3 variables I'm accessing round robin repeatedly, right, in a loop that runs for a long time. So we can ignore compulsory misses because we've seen these addresses many, many times. The question now is, what kinds of misses am I getting? If my cache was an optimal cache of 2 lines that was fully associative and optimal replacement policy, what you would see is all those misses would be capacity misses. But because I have they all map to the same set, but it turns out, all 3 of those will actually be capacity misses because even if I replace I can't fit all 3 in the cache at the same time anyway. So regardless of what it... But it... Right. The cache is not full, but the capacity is not big enough to hold all 3, even if you had the optimal replacement.
Okay, so the cache does not have to be full for it to be a capacity miss. Yeah, okay, but like for our, like we could have cache and we brought out our for like experiment, and it doesn't have to be full for it to be.
Yeah, so I think that the confusion here is that these kinds of charts, like I said, are used for analysis, understanding systems. When you get to a specific system, if I looked at the address trace of that program, I could then ask, for a given cache size, what kind of misses am I going to get? And that would tell you that for a 2-word cache size, I'm going to get all capacity misses, right? But when you actually instantiate, this is my actual cache system, and I look at what happens, I see, I'm not using some of the space. So it's not a capacity miss in that case. It is a conflict miss because of that particular configuration is experiencing conflicts, right? But those are not, all this terminology of 3 Cs are applied to this kind of analytical view of that program. Informally, we also use them to describe a particular system as it's running. We'll say, this must be a conflict miss because these 2 requests conflicted, right? But if you think about it, in any cache, whenever you get a miss, something conflicts because you kick something out. Any real cache, you always evict something. So you could say everything's a conflict miss. How do I know the cache isn't full? That other data sometime, a million cycles in the future, I might touch that other location, right? So, I think it's the difference between analyzing the program running on a system in general. For a given cache size, what kind of misses would you get versus a particular instance? So if you think about any cache when it's running, everything's going to look like a conflict miss because you evict something, right? You don't know whether the cache is full or not in general because you don't know the future. Is something else going to touch something that's in that other cache space? Maybe if it's invalid, you could say, in that case, it must be a conflict miss because I could have stuffed it over there except for my mapping strategy, right? Yeah. Okay. Yeah, unfortunately, when we talk about it, we talk about this analytical level. When we look at real systems, there's a lot of intuition about, that's probably, the question about if I made the cache bigger, would those misses go away? If I improve the associativity, would those misses go away? So I think it's simple. If it's a conflict miss, if I improve the associativity, would the misses go away? In this case, it wouldn't. Right? You still don't have enough capacity. Right. Okay. All right. See you on the midterm.